Hello everybody, this is Frank Block and you're watching Hiding Process Memory via Anti-Forensic Techniques. This talk is based on the research that I've done together with Ralf Palutke, Patrick Reichenberger and Dominik Stripajka from the University of Erlangen-Nürnberg. So this was a cooperation between the EMW research and the University of Erlangen-Nürnberg. To the agenda, we will start with a short introduction, some technical background, then dive into the subversion techniques. There are 3 of them. Then we'll talk a little bit about challenges and some considerations. After that, we'll have a look at evaluation. So we evaluated our techniques with memory forensics and live forensics techniques. After that, we'll talk about and have a look at detection approaches, evaluate those 2, and at the end, some conclusion. There's some related work that I wanted to mention, also to give you an idea what this is about and what is different from them. The first great research that I want to mention is Shadow Walker by Sherry Sparks and Jamie Butler. So what they basically did was changing the mapping between virtual and physical memory. And by that, any subsequent access to a virtual address would not end up anymore at the actual physical content for that virtual address. We are doing something similar, but there are 3 major differences between those 2 approaches. On the one hand, Shadow Walker only focused on the kernel space. It required a hook in the page fault handler in order to work. And the third difference is that it doesn't work anymore on current CPUs, so sadly or luckily. And the second related work that I wanted to mention is Gargoyle by Josh Lospinoso. He concentrated on the process address space, so similar to our approaches. But his approach doesn't hide the actual memory content, but he changed some characteristics of the injected code, in this case the executable state, and by that tries to hide from detection tools. Our approach is here in this case different. We are solely interested in hiding the actual memory content, so we don't change characteristics. The memory is still executable, for example, in some cases, but the actual memory content behind it is hidden. Okay, let's talk about a little bit about some technical backgrounds. So the process address space contains different data, executables, DLLs, shared libraries, or heap, stack data whatsoever. And all those memory areas are described by what we will call in this context memory area structures. So MES structures. On Windows, those are virtual address descriptors. On Linux, those are virtual memory areas. And as you can see, one thing that both those types have in common, both those structures have in common, is a start and an end pointer. So you can see here that the start address points to the beginning of the memory area and the end pointer to the end. And normally, every memory in the virtual address space of a process is described by at least one, or ideally by one memory area structure. So the second part that we're going to talk a little bit about is the paging structures. So the process of translating a virtual address to a physical page frame. The relevant part for us here in this case is just the page table. So at the end of the translation process, we will end up for a virtual address on a specific PTE, a page table entry. This one contains a pointer to the actual page frame that contains the memory for this virtual address. And the virtual address also has a page offset into this page frame where the actual byte is located where this address points to. And yeah, exactly. This is something that we are going to tamper with. Also to mention right here now is on both operating systems, on Windows and Linux, there are some reverse mappings. So on Windows, there's the page frame number database, and on Linux, the page structures. And those are more or less the physical point of view on the memory, but we will dig a little bit deeper into those 2 types a little bit later. And the third part is shared memory. So the idea of shared memory is to just share data between different processes. And the relevant part for us here to mention is that shared memory, as in contrast to private memory, is still accessible if the shared memory has been unmapped. So if it's not part of any process, for example, anymore, not mapped in any virtual address space, it can still be resident in the physical memory and can still be remapped as long as at least one process has a handle to the shared memory. So that's something to keep in mind. And there are different ways to create shared memory. On Windows, there's especially this API sequence. On Linux, there are at least 3 different ways to create shared memory that we had a look at, and we will see later. Okay, let's start with our subversion techniques. In general, we are trying to hide process memory with those. Those techniques can be used independently or can also be combined. And our scenario is, for example, an attacker that injected code into another process and now wants to hide this memory, or he wants to hide memory that is in his own process space. So the first technique is what we will call MAS remapping. So the idea was to do this technique is because that many tools, detection tools, depend on the information provided by those structures. So we rely on those. And this is why we wanted to remap some of the information, so to change the information in order to hide our malicious memory. One thing to note here is that this technique will require kernel level privileges, so this is something to keep in mind. So we are here right now at the beginning with our malicious memory. And we are now trying to hide it by just simply changing those pointers here. So you can now see here the effect. So what we did is we placed some benign data in the beginning, which is not malicious in any way. And we are changing the pointers in that way that the malicious memory, which is placed right after, is not described or not contained in this area. So they're not described by the VM end and VM start. They are not in this range. So there's no MAS structure anymore at this point of time that is including this memory area right here. But still, it can still be accessed, especially by the CPU executed, because the CPU doesn't care about the MAS structures. It only is interested or uses the PTEs in order to do the translation and to access the memory. And those are still valid and are still there. So this works after this modification fine. One advantage of this technique in regards to the other two that we will see right now is that it is not necessary to revert this modification in order for the malicious code to execute. So the second technique also requires kernel privileges in order to work, and it also requires restoration. So it is necessary to all the time unhide and rehide the memory in order for it to work. And we will talk about 2 different flavors of this technique. So we are calling them PTE Subversions, and we have the PTE Remapping and the PTE Erasure. And the beginning in both cases is the same. So we have here our malicious page, and we have a benign page with data that is not malicious at all. And our goal now is to remap in the first technique, to remap this virtual address to this benign data by simply changing the PFN. So there's a field, this PTE, that points to the physical page, and we are just changing this value so that this virtual address does it from this point on point to this benign data down here. And this page here has no PTE that points to it, is not mapped in any virtual address, and hence can't be accessed simply by enumerating or accessing virtual addresses anymore. The second technique is what we call PTE Erasure. So in this case, we are nullifying, so we are erasing the PTE, just putting zeros in there. So there's also in this case no more reference to this malicious page. It is not mapped in any virtual address space anymore. And any access to this virtual address will end up in no memory, which is not a problem per se, because this can be for valid reasons the case. For example, if the page has not yet been accessed, then this would look the same. So it's not suspicious by itself if there's a virtual address that points to a PTE that is 0. And the third technique that we want to talk about is shared memory subversion. So the idea here is now to use shared memory in order to hide our malicious content. And it is not to mention. I want to mention that it is not necessary to share memory between processes. Shared memory can also use solely by one process, and this is also the way we are using it. Our evil process does use this memory more or less like private memory, but with the advantages that come with shared memory from the attacker's point of view. So what the attacker does is he creates a shared memory segment, puts his malicious code in there, and then in the first step unmaps it, so it's not visible anymore. And then after that, anytime he wants to use it, he will remap it and again. One major advantage of this technique is that it doesn't require any kernel privileges, so it can be used with solely standard user privileges. So the attack process after we have set it up is more or less like this. As soon as the evil process wants to execute or access the malicious data, it shortly unmaps it into its memory space, executes it or reads data from it, and then unmaps it again. And by that, we successfully hide from most of the tools, or from nearly every detection tool that we evaluated, by simply with this simple trick. So why is that this memory can't be detected by any of the tools that we will see later? Let's dig a little bit into the details. So with the unmapping, what happens in the background is that the page table entries for this shared memory are zeroed. So they are not pointing anymore to the malicious pages. But there must be still some reference to it, because it is possible to remap those pages. So there must be some kind of reference to them. This reference is more or less hidden behind this memory handle that the process keeps in order for the pages not to be erased. In the case of Windows, this memory handle is a section object, so a pointer to a section object. And this section object, this section structure, is located in the kernel address space. So if you're following the section structure, we are getting to a control area field. This one points to the control area structure, which is more or less pointing to the file, if there's a file related to this memory area. And right after that, more interestingly for us, is a subsection structure, or there can be multiple ones. And those are pointing to the so-called prototype PTEs. And this is the interesting part for us, because those prototype PTEs contain the actual pointer to the malicious pages. So the reason why we don't find this malicious memory also if we scan the kernel address space is that the pages are not mapped into the kernel address space. So those prototype PTEs are not part of the page tables for the kernel address, for the kernel. So they are not mapped into the kernel address space, but only those prototype PTEs itself are part of the virtual address space of the kernel. So it's just data lying in there, those PTEs. They are not part of the page tables itself for the kernel. And that means that those pages are not mapped into the address space, and hence the memory content can't be found when searching the virtual address space. Okay, let's have a look at the evaluation. We implemented our techniques for Windows and Linux and tested those in multiple VMs for Windows and Linux, in both cases on x64 architectures. And this is those are the results for the memory forensics point of view. We used multiple plugins. We used YaraScan plugins. We used recall and volatility for all those plugins. And what you can see for YaraScan, for example, is that volatility's YaraScan was not able to detect any of our hidden malicious content, but recall did. The reason is that recall does a raw search, so it doesn't rely on any virtual address structures, virtual address translation structures. It only searches the raw memory, and by that he finds our hidden code. But obviously this only works if we know upfront what we are searching for, so it doesn't work as a generic method. We also had a look at some dumping plugins. So we dumped the memory content of the processes, and only in the case of the MAS remapping and only with volatility we were able to find our malicious code in there. With the other tools and other plugins, it was not the case. And also we did find our malicious code by if we accessed it directly. So if we used recall or volatility, the interactive shell, and did a read for the virtual address, in this case also it was possible to detect the malicious memory, but only in the case again for MAS remapping. And a third time again, with PTE num, we were also able to find our injected code for MAS remapping. But besides that, in all other cases, our malicious code was not found by any of those plugins. In some cases, there were some indicators that could maybe give you a hint about something fishy going on, but the actual memory content was only detected in those cases that I mentioned earlier. So from a live forensics point of view, it gets a little bit worse. On the one hand, we also used the tool Yara and scanned all the processes. None of our hidden memory has been detected by Yara. We were able to detect our malicious content in the case of MAS remapping again with the debugger, but only on Windows. So with the WinDebug tool, we were able to find our malicious content by searching and also by directly accessing the virtual addresses. But besides that, none of those approaches were able to find our hidden malicious code. We tried dumping the process address space with debug, with GDB, with WinDebug, also used Process Explorer on Gcore, but our malicious content wasn't in those dumps. But at least in some cases there were errors pointing out that some of the addresses seemed to be something wrong with them. So there were some indicators, but the actual memory content was only detected in those two cases for MAS remapping and not in the other cases. And also to mention, the shared memory scenario with shemget on Linux was not at all, in any case, in any way detected by any of those plugins or tools. Okay, let's talk about some challenges and considerations, some things that you have to consider when you're implementing and using those techniques. On the one hand, as mentioned earlier, for PTE subversions and shared memory, we need still some control code that has to be somewhere, so this could be detected. In order to unhide and rehide the memory. We did also lock our memory in order to prevent any interferences from page swapping. And also to prevent any side effects, we are undoing all our modifications right before the process exits. Also, especially on Linux, there are some fields that you want to have a look at and might, in some cases, that you might have to adjust in order to prevent side effects, especially if you're not undoing the modifications. Then there are some counters that you might have a look at and might have to adjust in order to prevent any problems. Okay, let's talk a little bit about a problem on Windows with the standard PFN remapping. So if we are doing the PFN remapping as explained earlier, this will lead to crashes, especially if we, for example, scan the process with Yara. Then it pretty reliable crashes after the PFN remapping. So we came up with a little workaround in this case. This is an initial situation, so the PTE points to a malicious memory. And what we now do in order to prevent the detection is to, in the first step, to erase it, similar to the PTE Erasure, but we added some additional steps. So what we then do after that, we are doing a read access to this virtual address, which will lead to the creation of a new page, because the operating system will think there's not yet been created any page for this virtual address, so we are creating it. That means that after that we have two pages which correspond to this PTE. And after that we are simply switching between those two pages in order to hide and unhide our malicious memory. And by that we are preventing the process from crashing if Yara scans it. There's still some issue left with this approach. It blue screens as soon as the process exits. We have not yet identified what exactly is the problem with that, so this is something to be done and will be hopefully fixed in the next few weeks or months. So let's talk about memory subversion detection. First, MAS remapping detection. What we are using here are the paging structures. We are enumerating all the page tables and examining the page table entries. Each page table entry corresponds to a virtual address. And by examining the page table entry, we know which virtual addresses are currently valid, so they are referencing page frames that are currently mapped. And we can use this information to check whether or not they are virtual addresses which are not described by a VM area structure but are valid. So in this case, we have those two virtual addresses which seem to reference valid page frames, so there's actually memory content behind them, but they are not part of any MAS structure, so that's something suspicious which we alert on. Now the PTE Subversion detection on Windows. It's on Linux a different story, so we are splitting this detection in two parts. On Windows, we now have here the initial situation. So the malicious PTE points currently still to the malicious page. And in this case here now, we have also the physical point of view on the memory, the PFN database, which we mentioned earlier briefly. This is just more or less just an array of MMPFN structs, which are indexed by the PFN number. So the PFN here points on the one hand to the page frame, and to a MMPFN struct over here. Each MMPFN struct for a valid page also points back to the PTE that belongs to it. So we have here a kind of loop that points back and forth. So if we're now doing the PTE remapping, so we are changing the PFN value, the pointers get modified. So we are now pointing at the benign page down here, and we are also referencing another MMPFN struct. So that means we have a broken loop. We have a valid loop down here because this MMPFN struct belongs to a valid page. The benign page is already there. And we have a valid loop here. But we have also the pointer from over here, which does not point back over here. So this is something that we can detect on. Also, by enumerating all the MMPFN structs, we will encounter this one here, which points to this PTE, but the PTE does not point back. So this is also something that we can detect. And the third part here is the PFN number. So by enumerating all the PTEs and collecting all the page frame numbers, we can detect duplicates. And by that, the PTE remapping. This only works for shared memory, for private memory. With shared memory, this doesn't work because with shared memory, it's quite common that multiple PTEs point to the same page frame. Also, this detection here does not work with shared memory because for shared memory, those MMPFNs don't point to this PTE, but to the prototype PTE. So we don't have this loop that we can detect on. So these detections here only work with private memory on Windows. The detection that we will now see in a few seconds on Linux does work also with shared memory. Okay, now the last slide for Windows. In this case, we see now our modified PTE remapping, because the original one, as I said, crashes when Yara is, for example, scanning the process. So this is the situation. The detection is more or less the same. Only the situation is a bit different. So we can see now here we have our PFN value, which points at the second page, which has been created for this PTE. So the also created MMPFN struct points back to this PTE. So this loop here is fine. It points back and forth validly, so there's nothing suspicious here. But there are two things to mention over here. At the one hand, we have again an MMPFN struct which points to this PTE, but this PTE doesn't point back. And also we have two MMPFN structs which point to the same PTE. So those are two characteristics that we can detect on. Okay, let's now look at Linux. The point of view on the physical memory on Linux are the page structures. So there are several page structures which are more or less also indexed by the page frame number. And by enumerating those, we can collect page structures which belong together, and also physical pages by that matter. This is done by looking at the mapping object that is referenced by those page structures. This mapping object is also referenced by the VM area structures. So by this mapping, we can correlate pages with their corresponding VM area structures. A little thing to mention over here, there can be multiple mappings per VM area structure. At the one hand, a mapping can be referenced by the F mapping. So this is the case for files that are mapped. And also in this case, there can additionally be the anon-VMA chain pointing to mappings. There can be multiple ones. This is especially the case when forking and when using copy and write protections, and then getting private copies being created. Those are then referenced by those mappings, so there can be multiple ones. That's just something that we have to keep in mind when investigating this issue, that we have to collect all of them. Behind those mapping is, in this case, for the anon-VMA chain, are anon-VMA structs, and for the F mapping, it's an address space struct, but this detail doesn't really matter for us. The only thing that we are interested in is the object itself, which we can use to correlate the page structures with the VM area structure. So the fields of those mappings are not really interesting to us, just the object itself. Okay, now let's have a look at the other side. So when we are now enumerating the virtual addresses for a VM area struct, we can resolve them to the page frame number, and by that get the corresponding page structure. And again, we can collect them based on the mapping. And in this case, we have 3 virtual addresses with the 3 page structures which belong to this mapping, which also corresponds to the mapping for this VM area structure. If we are now looking at our attacks, in this case, the PTE Erasure, the initial situation is that we have our malicious page over here, which is still referenced. Now we are erasing the PTE. The pointer goes away. And when we are enumerating the virtual addresses, we now only get 2 pages because this one doesn't belong to any page structure anymore because it doesn't have a corresponding PFN. So when we are collecting those for this VM area, for the virtual addresses, we only get 2 pages for this mapping or with this mapping. If we, on the other hand, enumerating all the page structures, collecting them based on their mapping, and then looking for each VM area struct for their corresponding mapping and the pages, we will see that we will end up with 3 page structures. So we can clearly see a diff, 2 on the left side, 3 on the right side, and this is something suspicious which we alert on. So, and the last step is our shared memory subversion detection. It's more or less the same on Linux and Windows. We are basically just enumerating all the shared memory handles and looking for those which are currently not mapped into the virtual address space and alert on them. On Windows, we are additionally checking for the executable permission. So we are only alerting on executable memory because there would otherwise be a lot of false positives. On Linux, we are not checking for the executable state because it's not a reliable way to detect this kind of memory. And hence, we also have some false positives on Linux, which we'll see later. Okay, let's now talk about detection, about the evaluation of our detection approaches. We use the same environment as for the memory subversion evaluation. Additionally, for the false positive evaluation, we started several browsers, Office applications, and also PDF documents. And this will, the results of that we will see a little bit later. Okay, here are some examples for detection on Windows. In the first case, we have an output of our recall plugin for the standard PFN remapping, so not our modified version. So how it would look like in the output if we would use the standard version, and also for the PTE Erasure. So the first 2 entries here are an output for the PFN remapping. So we can see here in the .pfn column that we have a true for the first 2 entries. So there, we can see also here in the PFN column that there's in fact the same PFN value for those 2 entries. And what we also can see is a true value for the PTE pointer diff, which means that the PTE with its PFN points to a certain MMPFN struct, but the MMPFN struct does not point back. So we have a diff over here, and this also means that the second entry is the malicious one, or most probably the malicious one, because it has the value true in this case. And this, the third entry is an example for the for the PTE Erasure. We have in the column 0 PTE a true. We can also see that the PTE value is actually 0. And this means that we have a MMPFN struct identified, which is valid and points to a PTE, which, however, has a PTE value of 0, which shouldn't be the case. And this is something that is detected over here. And the second example is an example output for MAS remapping. So in this case, we have in the column orphaned page a true value for those 2 virtual addresses, which means that they are currently valid, but not described by any MAS. Here are some examples for the evaluation on Linux. First, PTE Remapping. So here we can see output, essentially 2 mappings that have been identified by our plugins. The first case is an false positive. So we have in the systemd journal process, we have some mappings that are reported here, but it is not an attack. So there's no subversion technique that has been the result for this. So in Linux, we have quite some false positives in some cases. But the second output is in fact a result of our PTE Subversion attack. So we have 2 pages which are not referenced by the virtual addresses, but are part of the page structures. So this is detected over here. And the last output here is an example for shared memory on Linux in this case. So we have a shared memory handle, which is currently not mapped in any process, or not in this process. So this is reported. Okay, now let's have a look at false positives. First, Windows. Regarding MES remapping, there have been some false positives in the context of Chromium. So there were pages which are not described by any MES structure, which is interesting, and we are planning to have a closer look at. Regarding PTE subversions, there are no false positives at the moment known. At least we didn't find any in our test environments. And regarding shared memory subversion, there can be false positives. Obviously, if the process has a shared memory handle but does not have this memory mapped into its address space. But in our test environment, we did not encounter any shared memory segment that is executable or not mapped at the moment. With Linux, MES remapping is not implemented yet, so we can't make any statements there. PTE Subversion on Linux, there were quite some false positives, especially for the Firefox and for the systemd journal process. So this is something that we are trying to optimize in the next time. So hopefully we'll come up with a solution for that. And regarding the shared memory subversion, in our test cases, also again with the Firefox, we had quite some false positives, 40 shared memory segments that were reportable by a plugin. So that's also something where we might be able, hopefully in the future, to improve the output. Okay, let's come to the conclusion. Here we can see a simple short comparison of the techniques from an attacker's point of view. We already mentioned all the advantages and disadvantages, so it's just for the documentation. To conclude, with this research and with this talk, we introduced 3 novel subversion techniques which are able to hide memory from memory and live forensics on Windows and Linux. We are releasing with this talk also some proof of concept implementations for both operating systems that implement our subversion techniques, and our plugins, the recall and volatility plugins that we've implemented, which are applying the detection approaches which we have described in this talk. And those are all referenced in the next slides where you can grab them. Some limitations. We still have the issue for the subversion with the blue screen in Windows with our PTE subversions. So this is something that we need to fix. Also, the detection approaches for the PTE subversions on Windows can be circumvented by shared memory, by the usage of shared memory. So this is something that we have in the future to have a closer look at. Also, there were quite some false positives with Windows, with Linux, with the detections. So that's something that's not ideal at the moment. Also, an additional problem in Linux, there can be page instances, so page structure instances that have no corresponding mapping. And by that, it's not possible for us at the moment to detect those pages in regards to subversion techniques. And also, again, on Linux, our PTE subversion detection implementation is at the moment quite time-consuming. The main reason is that we have not yet implemented the MES remapping detection, because the same approach for that is also used to speed up the PTE subversion. So as soon as we have implemented that, also the PTE subversion detection should be faster, but at the moment it's quite slow. Okay, some words to future work. One thing that we want to have a closer look at is different ways for mapping shared memory, especially using subviews, and by that maybe circumventing our detection approaches. Also, we want to resolve the Windows crash, obviously, and we are also wanting to have a closer look at the new Windows 10 memory combining feature. So this might be something that interferes with our detection and subversion techniques, and we should have a closer look at. And last but not least, manipulating everything that we've used for detection so far. So the MMPFN structs, page structures, messing with those might be interesting to look at in order to prevent the detection from being successful. So with that, thank you for your attention. If there are any questions, hopefully we have some time for them. Here are the resources, so all the links to all the proof of concept implementations and plugins. And with that, are there any questions? Okay, hello everybody. I hope you can hear me fine. I'm not sure if it's working right now because my screen freezed here. And now I see there's a movement. Yeah, hello? Yeah, I started to talk, but I'm not sure if everybody can hear me. Maybe in the chat, someone can tell me if you hear me fine. Yeah, but do they hear me? Because I don't see any reactions in the chat. Okay. Yeah. Yeah. Hello. So if there are any questions, feel free to do it in the chat. Otherwise, thank you for your attention. Hope you enjoyed the talk and the rest of the conference. Ah, yeah. Okay, now. Yeah, thank you. I see now that you can hear me. I had a little delay in the chat, so I was not sure. Okay, thank you very much. So I don't see any questions right now. Then yeah, feel free to contact me. There's some contact information in the GitHub page. Feel free to email me. My LinkedIn handle should also be in my profile. So yeah, if there are any further questions later on, feel free to put a question somewhere in the mobile world. Otherwise, yeah, enjoy the rest of the conference. See you. You too. Thank you.